So, last thing we did was we created exceptions for our course. So exceptions would be an error that would happen, and whenever that error is thrown, whoever is using my function, add student in this case, will have to handle that error, that issue. Okay, and we could have thrown it different ways. We could have thrown it in a thing where, just like let's say, just like the scanner. Where was the scanner? It was here. In this case, this this input mismatch exception doesn't need to be caught. Okay, so there's different types of exception that you could have. In this case, this exception doesn't need to be caught at all times and whatnot. But we don't need to delve into that for too long. Just note that all exceptions need to inherit from exception. And if we catch the parent exception, which we're going to talk about in inheritance later, well, then we're catching all of the exceptions, and this is kind of bad, and we'll come back to that later. Okay, but for now we could ignore all of those. So understand that anything we put in the try catch is we understand that there's a possibility of an error happening, and if it does, we're going to deal with it, right? So the one who's using add student, I'm not add student itself, we're not dealing with here, because we don't know how they want to use our add student function, right? Think about these functions, think about it in all the different scenarios that it's possible. Sometimes maybe they want to say, hey, you know what? The max amount of students, we're going to increase it because of this student, right? We can't expect how they will deal with it. So we don't want to deal with this issue inside of that function. We want to allow whoever's using the tool to deal with the issue. So this is an important factor to understand. Okay, so this is good. Let's take care of that. Let's extract it. Let's go to the next part. So extract method, I'm gonna give that to custom exceptions. All right, so that's good. There's a couple of things we want to talk about. So we talked about the errors, that's perfectly fine. Compile type, run type, and logic one, which is the worst. Another thing I want to talk about is recursion. I don't know if we need to right now. You could probably go without recursion, okay? But I'm going to show you a different type of thing you could do, which is called recursion. And let's say an example. Let's do an example, an easy example that you always see. Let's say a factorial of a number. I don't know if you guys know what factorials are. It's basically inside math. If I put, let's say, if I put 4 exclamation mark, this means 4 factorial, which basically means 4 times 3 times 2 times 1, which gives you the final answer of, let's say that's 6 times, well actually that's a lot of numbers. 4 times 3, 12, 12 times 2, 24, right? If I put in, let's say 8 factorial, you would get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Which would give you a big number, etc. Actually, let's go ahead and do a calculator. Let's say 8 factorial. 8 gives you this huge number, which is all of that. Cool? So this is factorial. Now, if you think about this for a second, how would you build your application to manage factorials? Well, first of all, we would see a couple things. The first thing is we're given a number, and with that number, we could give back the final results. All right, so we could create a function right now. Let's say private, I can't spell, static, it gives back an integer, right? That's the final result. And we need a factorial of a specific number, and let's keep it to integers. So in this case, the initial number, which is 8. So we'll give the number. And inside that, when we get given the factorial of 4, so the number is 4, or when we're given the factorial of 8, the number is 8, we want to start at that number and reach number 1. And the number 1 is kind of useless. Anything times 1 is the same number, right? So we could ignore 1. So we want to do 4 times 3 times 2 to give you 24. We want to do 8 times 7 times 6 times 5 times 4 times 3 times 2 to give you this number, right? How would you guys do this? This is something you should be able to do in the blink of a second. So how would you guys do this? Any ideas?
For loop, sir.
Yeah, basically a loop. We're repeating something, and because we know the amount of times we're doing it, he perfectly said it, we want to use a for loop. So tell me, inside my for loop, at what number would I start? So my initialization, what would it be?
Sir, number.
Number. So you know what? We could actually skip this part because number is given to us, right? We could totally ignore it. Okay, we're doing this loop how many times? Until when?
Less than. When number is less than 1.
Number is
greater than 1.
While number is greater than 1. So we want to keep doing it until 2 is reached, but when it's reaching 1, we could ignore it because this doesn't change anything. It's actually an extra work for a computer, and we want to optimize as best as we can, right? So doing the 1 wouldn't hurt, but at the same time, you're doing an extra step for no reason, right? Rather than staying at home, you came to school to watch a video. Why? You don't need to watch a video from school. You could watch it from home. It's the same thing. Right? That extra step doesn't hurt you, but it slows down your day, your work, etc. So we don't want that. So the first part is initialize, and in this case I have nothing to initialize because the number is given. The second part is while number is bigger than 1. And the third part is increment, decrement. What should we do?
Number minus minus.
Yeah. And we want to keep that minus minus in front of number rather than after, because this is a bit faster, okay? And I don't know if we talked about it, but just do the pre-term, okay? If you're gonna use that, or just make it number equals number minus 1, either or. Now,
so result is equal to number multiplied by number.
Result equals number
is equal to 1 sec. Result is equal to result multiplied by number.
Result multiplied
by number.
Okay. What result doesn't exist?
Yeah, we have to create a integer.
Right here?
Yeah. Now we can return it.
Where do I return it?
Return it.
So we have to initialize result with 1.
Okay, so do I do
so there will be a
like this? Sorry, I couldn't hear the part about the return. I think you said
return result.
Like this?
Yep.
Anyone sees any errors? Actually, first of all, my compiler is giving me a little red squiggly here. I don't know if you guys are seeing it.
So we can return it after the for like body of for. Okay. So there will be a
return
result.
Result again?
Yep.
I got another error. If I put
we have
result should be initialized out of the for loop.
Yep.
All right. Remember the scopes, right? So inside the for loop, whatever is created gets deleted. And the worst part is it's created inside the body, and the body is called multiple times. So this thing is redone multiple times. So we want this to be outside of the for loop. It's right there. So like this gets created once, and the loop does not create a new result every time. So result is equal to 1, and then we go and
we have to remove.
Sorry.
So we have to remove result from the for body because in every like iteration it will return the result, and we don't want.
Actually, you said it correctly, and at the same time incorrectly. He is right. At every iteration, it's going to call the return, but the problem is the moment you hit return,
it will be only one iteration.
Exactly. It would end your function. So it wouldn't continue to the next iteration. It would end this factorial function right away. So this part is no good. So we want to do this really at the end, right? Because the moment you hit a return, ends the application, ends the function, not the application, ends the function, right? If we hit a return inside our main, that would end the application because our main is the application, right? The entry and the exit of our application. So now coming back to this. So we got a factorial. Let's see if it works, this factorial. And we got two numbers already we know of, the 4 and the 8. So if I call factorial here and I give it the 4, I should get a good number. And if I do, again, factorial and I give it an 8, I should get those two numbers that I see there. So let's run that. And look at, what do you know? We get 24 and we get 4320. Perfectly done. Good job, guys. Okay, let's try a couple other numbers. We want to always make sure that our thing works. So put another one here, maybe 0. What would 0 give you? And maybe -5, right? And again, we run it. Is this correct? So 0 gives us 1 and -5 gives us 1. So I'm not too sure about math, something I don't do every day. Maybe I'll go and Google it. So let's say we have 8 factorial. We had already that number. That's perfect. What if I have 0 factorial? Okay, it gives us 1. So our answer here is perfect for the 0. What if I give -5? -5 should have gave us -120. How can I fix this? Again, I'm showing you this because we should never assume that our application is correct unless we test it out with varied numbers to make sure that we don't have a mistake. And again, the more precise you are, the more throughout you are with this, the better you're gonna be as a programmer, the more people are willing to pay for you, right? This guy doesn't get any issues. He makes sure he checks every little corner. He's the guy we want to get. Otherwise, we're going to get errors along the way. Maybe not now, maybe in a year, maybe in a couple months, whatever the point is. When we get those errors, it's much harder to look for them and figure out where the issue is than when we are building it, right? So this -5 should have gave us -120. -5 is the same as 5. Right? The only difference is because there's a minus, we should have still went further. But because here number is less than 1, right? We can't do it. What should I do to fix this? What should I fix inside this code? This could be a good quiz question. Anyone?
One sec, sir, I'm thinking.
Amita? Okay, thank you. Sorry, you have a lot of music in the background. Anyone? So, the minus in this case, well, the minus and the positive, they both give 120. The only difference is one is -120 and one is +120. So here, a couple things we could do. This result is fine. We'll keep the result there for a second. But we could do something else. If, in this case, we know when the number is less than 0, right? So negative. When the number is less than 0, we could do two things. One, we could make the results into, actually, we could make the results, well, let's just do it straight up. We could make the result into -1, right? And the number, we could multiply it. So this is the same as saying number multiplied by -1. And if you remember, anything multiplied by minus will be minus. So if there's a minus number multiplied by minus number, it will be positive. right? So this is minus 1 multiplied, let's say minus 8, will give you positive 8, right? So what we're doing here is we're making the result start at a negative number, and we're making the current number, the starting number, a positive number so that we could reduce it, right? And you'll notice that minus 5 gives you a minus, but if it was minus 4, it would give you, well, minus 24 as well, right? So let's try this out. Let's see what happens. So now if I run it, I get minus 120. If I do, let's do another number. I don't know, let's say minus 10. This number, let's make sure it works, minus 10. I know Google works, so 3628800. Perfect. Cool. So far, so good. Any questions? Hopefully you understand what I did there. This number is a counter for us in our for loop. So it starts out at 8 or whatever number given, and it decreases to 1, towards 1, right? Decreases towards 1. Well, if that number is negative, well, it'll never decrease to 1. It'll have to increase to that number. So in that case, all I did is I flipped the number from negative to positive, and I flipped my result from positive to negative. So now the result, every time it gets multiplied, is going to keep the negative number, but it's going to keep moving to the next iteration of the number, whatever that is. No questions? Make sure you understand this, because now we're going to go ahead and remove the for loop and go use this thing we call recursion. Okay. So no questions? Okay. So we're going to call this one, we're going to rename it to factorial loop, okay? And we'll come and fix that. Actually, let's go ahead and use the refactor. As I always tell you, use refactor. So rename, and we're going to call it factorial loop. 1, 2 O's, there we go. And let's do the same thing with this thing we call a recursion. And then the recursion is the same. Well, it's not really a loop, but recursion is basically calling itself, right? And you're going to see it. I'm going to show it to you. It's going to make more sense than if I explain. And the cool part about recursion, the first thing that's cool about recursion kind of makes your code a bit more cleaner. I can't spell recursion. Cleans up your code a bit. The bad part about recursion is it's really intensive on your system. So you probably most likely will not want to use this doing production for any real application. This is good if you go to an interview and use recursion, because it's much simpler, much readable than a loop. Okay, so this part should be good for, again, your interviews. And it's also good to understand that recursion is not something I want to use inside real production, because, hey, my system is going to get slow. There's a limit to how big my stack could go. This also uses the stack a lot. We'll look into that too. So it has a limit, and you're going to see that in a second. And let's try it out. So the first thing we're going to do is, again, create a function, private static int, let's say factorial. And factorial will take, again, a number. It always needs a number to start with, right? But inside of a recursive method, inside of a recursive function, rather than looping through numbers, when we need the same thing being done multiple times, we want to use itself. We want to use factorial itself. Okay? So what we want to do is that we understand a factorial is this. We understand that a factorial is a number that gets multiplied by the next lesser number until it reaches the end. And the end, we concluded that it's either 1 or 0 or, well, 1 or 0 basically. 0 and 1 will both give you 1, right? We did that with this example here. And we did it in Google to make sure it was correct. In both scenarios, we saw that the end result was 1. So what we need to do is when we're doing this factorial, when we're doing this recursively, what we're going to do is take the current number and multiply it with the function again. Let's call factorial f, okay? And then we pass it the next number, right? And what the next number is going to do, is it's going to replace itself with that number and replace it with the next thing. And it's going to keep on going down until that number is 1. That's the moment we finish, right? So inside of a recursion, we need to start, well, this is usually how we do it. There's multiple ways of doing a recursion. For now, you just want to understand it. Later on, you'll get into the different types of recursion. Actually, I'll write the types of recursion here, and then maybe we'll explain it. Sorry, I just want to get this out of the way. So let's say the first type is this thing we call the direct recursion. So basically, it calls itself until it's solved. Basically, so a good example, it would be. Actually, we'll do it here. Okay, so this is the one we're doing it here. Other than that, we also have indirect recursion. So, to be honest, I don't think I need to go through these, to be honest. This is when a method, like factorial, will call another method, factorial loop, which would also call back factorial. So it's kind of an indirect recursion. It's someone else, but it brings it back to you. To be honest, we're going to, you know what, we're going to delete that. We'll come back to this hopefully in the future if we have time. So what we want to do for this is, first thing we want to do is specify the end. So at the beginning of our factorial, the first few lines, we want to specify the end. So the end of our factorial would be when we reach 1 or 0. And I want to mention both because it could have been that he gave the direct number of 0 right away, right? So if number equals 1 or number equals 0, well then the result should be 1. Okay? So the end is given first. And remember, we're doing the end first because all programming code is read one line at a time from top to bottom. So it's going to start with this. It's going to check, are we at the end? If we're not at the end, now this is what gets funky. If we are not at the end, we want to return the current number multiplied factorial number minus 1. So now we want to go one number down. So we're going to start with 8. It's going to get 8. Is 8 equal to 1 or 0? False. Right? So it's going to return 8 multiplied factorial 8 minus 1. So 7. So now it comes back with this. 7. Is 7 either one of these? No. So multiply 7 times this. And it's going to keep going down until it reaches the last number, which is 1. And then it's going to go back up. Do you guys see this? So we're going to test this out and we're going to go through it simply and you're going to see what I mean. So first thing first, let's change our test to do factorials only, right? Now, if this worked correctly, we should get the same number as we did with our factorial loop.
Hello?
Yes, Amanpreet?
Sir, in here, return number factorial, number minus 1. Sir, eventually the number will become 1. So,
Exactly.
sir, after it will return 1.
Yes.
Not, I think, not the result.
Well, when it returns 1, it'll go back up the levels, replacing all of these numbers with the specified numbers. And you're gonna see this. Let me run this first, and then we'll go through this code one line at a time. Okay? So the first thing we're gonna do is run this code. The first thing I'm gonna do is fix my errors. So you'll notice now I'm kind of stuck inside of a basically an infinite loop, but in this case it's an infinite stack, and my stack has a maximum space. So I get this type of error, which is called stack overflow, right? So it worked for 24, if you notice. So what are numbers? 4 was 24, that was perfect. For number 8, it was 40320, perfect. For 0, it was 1, that's perfect. But my minus, I did not take care of those. So I need to also take care of my minuses, right? So we need to do the same thing for our minus. So inside here, we're gonna do So this is a bit different. You know what? We'll come back to, actually, let's deal with it right now. So if we get a number that's minus, how should we deal with this? So if it's a minus, the final number, I want it to be multiplied by minus. So, so this wouldn't work. So if we come down to it and it's minus, let's say it's -4, it comes in, is this any of them? No. Number, factorial, because it's going negative, and that's the problem. Okay, so if it comes down and it's a negative number, so if number is less than 0, we want to make, first of all, let's open the parentheses. We want to make our number equal a positive number. So for now, we'll make this number multiplied minus 1. So it becomes positive. That's the first thing we want to do. And then we want to check. Then we're going to give a result, actually. Let's create a negative, positive, or negative, which is going to be 1, right? And if it's negative, we want to let us know by doing this. Okay, and the cool part about this is we could return that at any moment. So here we could do 1 time this, and over here we could also do that. Okay, sorry for this extra thing. This is just to make sure that we could get factorials of negative. So what we're doing is, again, keeping track that the number given was negative, and then we flip our number to become positive. Whatever the number is multiplied -1 will be the positive value. Okay, so the whole algorithm here of how it does it doesn't really matter, but let's press play. You'll notice that my numbers are correct. Cool. Now, a couple things we need to check. Let me zoom out a bit. If you notice, this part is my recursive, and this part is my loop. And if I didn't take care of negative numbers, my recursive would actually look much cleaner too, right? But the fact is, we want to apply for everything. So just to show you how it would look without the negative, it was a bit cleaner. This is how it would look like if we're not dealing with negative numbers. Okay, same thing for this. Just to show you again, if we have negative numbers, actually I want results. This is how it would look like comparatively. And well, you're gonna tell me, well, I like this better and you're more used to it, it's fine. But you're gonna see as we get these more complicated, right, like rather than factorial, we'll talk about what's his name? What's the guy's name? Fibonacci. There we go. Fibonacci created this calculation to calculate the amount of rabbits reproduction, which was completely false, but it was a really nice formula and it's being used for other things. But calculating Fibonacci in a loop is a really painful thing. If we get time, we'll do that one too. Anyway, let's undo this and let's try to see what happens. So what happens inside a factorial? So what I'm going to do is I'm going to put a breakpoint here, right? I'm going to click right beside the numbers. Actually, I'm going to click on the first line. Now, first time we're calling this function, the application is going to break for me at this line and wait for my commands. So I'm going to go and run. You should see a little bugger icon here, but for me, I'm going to go and click on debug, this little bug symbol. I don't remember if we talked about debugging yet, but we'll talk about it soon. And now the application is stopped here. And notice that the number given to us is 4. So this is the first time we're calling our factorial at line 19, right? With this breakpoint. So now the application is waiting for us. It's showing me the number given is 4. Create a variable here. So it creates a variable positive or negative and equals it to 1. Is that number is that number less than 0? False. So skip that if statement. Right, let's put that as much as we can see. Is that number our end? Right? Is it 1 or 0? No, it's not. Skip that part. And now look what it does. This is the key point. It's going to return positive or negative, multiply the current number, which is 4, multiply it. Look here, it's calling another function, and that function is itself. This is what recursion is. It calls itself again. And this is what's so important. So as soon as we have this, you could think of it like in math as a parentheses, and whatever's inside that parentheses needs to be finished before this line is executed. So the moment this happens, what happens is on pause. And look at here on my left side. This is my call stack. Okay, so this is something else that's there as well. Remember there was a stack and a heap? Well, this is called a call stack. And what's important here, first of all, we have a limit. You saw it when we went into an infinite, that we reached a limit. And this limit, you usually will not reach it inside of a loop. Okay, so call stack limit is a bit big. You notice that it started out at line 19 in main, where it called this function factorial, and on factorial line 45, it called factorial again, and now we're here. But you'll notice that this time number is not 4, it's 3. Why? Because we decrease number every time we call it. Okay? Again, is it a positive? Is it 0? No. Skip all of this. Is it 1 or 0? No. Go ahead and call it again. Notice that we have another function factorial in our call stack, right? And this time the number is 2. We check. Is it less than 0? No. Is it 1 or 0? No. Call again your function. Now the number is 1. Now this is our end. Remember, our end is here. So we check. Is it negative? No. Is it 1 or 0? Yes. So now we're going to return a value. Now look at it. We're not calling any more functions. So as soon as I do this return, it will look at my call stack. I'm currently at my number 4. My call stack ends, gives back the value here, which was, I believe, 1 or 2 or whatever it was. It was 1. So it'll be 1 times number times positive. So it'll give back 2. It'll give back that number to the previous stack as it's going back up, and keeps on doing that until we reach here, where in that case it will print to the console 24. You guys understand? Should we go through it one more time? Okay, let's go through it one more time. So not that one. So inside my factorial, I'm given the number 8, right? I check it first. If it's negative, it's not, we can skip that. Is it my end number when it ends my application? Notice it ends because we don't call any more functions in here. We're just returning a value. We're not calling another function. If it's not, go and call factorial with number minus 1. So number is currently 8. It's going to call another function. Let's go back to debugger. It was going to call the same function with the value 7. And we keep on going. Calls the same function with the value 6. We keep on going. Calls the same function with the value 5. It keeps on going until it reaches my last number, which is 1. And when it reaches 1, it reached the end. So return a specific value. It returns that value. Now it goes back up the call stack. So if you look at the stack, you're going to see it's going to keep reducing it because those functions are ending. It's returning. Remember that return ends our function until we reach our final number, and it's going to show on the console 4320. Any question? Okay, let's do it one more time with 0 and maybe with -5, and we'll stop there. So with 0, given that number, we check. Is 0 less than 0? Is it negative? No, skip that part. Is it the end? Is number equal 1 or number equal 0? Yes, it is. So return right away. So our application ended quickly, our function ended quickly. And you'll notice on the console, it will print 1. Now let's try the -5. Inside -5, is -5 a negative number? Yes, it is. Make number equal number multiplied -1. So if you look here, number is currently -5. That line makes number become positive. And this line makes our positive or negative become negative. So we track that. Is it the end of our factorial? No, it's not. Skip that. Now call factorial with the same number. So we do this, and it's going to go in a repetition like last time. And you'll notice the number is never negative again. It's only the first time. Right? So now we're at 1. Return that value, and now it keeps on going back up the stack to finally end it and show us the final value of -120. Anyone has any questions? Because I'm pretty much done with recursion. And again, maybe factorial is not the best function to do recursion, but if you do this Fibonacci, let me go grab that. If we go here and we write Fibonacci, this is the sequence. Let's see if we can find it here. If you program this, you'll notice that open. If you program this, you'll notice that it's much cleaner to do it inside recursive than inside of a loop. And if you don't know Fibonacci, is that you're given the first two numbers, the first two positions, which is 1 and 1, the value of those first position, position 0, position 1, and you add them to get the next position. So first position, second position together gives you 2, that's the next position. 2 plus 1 gives you 3, that's the next position. 3 plus 2 gives you 5, that's the next position. 3 plus 5 gives you 8. 8 plus 5 gives you 13. 13 plus 8 gives you 21. 21 plus 13 gives you the next, and so forth, so on. Right? So I would say this is a great exercise if you guys want to see how good you are in programming. This is something that usually would be a simple assignment when you're learning recursions and loops. Try it out and see how you do it. Actually, if you guys think about that, like, I'll do a quick one here. So let's say the positions. You got position 0, 1, 2, 3. Okay, let's say this much. And the values for those positions, remember that position 0 and position 1, you're given those values. So these two are 1s. The next position, 2, is the last 2 together, so it becomes 2. Position 3 is the last 2 together, so it gives you 3. The next one is the last 2 together, which gives you this one. Again, same thing, 8. The last 2 positions together would give you 13. The last 2 positions together, 8 plus 13 gives you 21. The last 2 positions together gives you 34. The last 2 positions together gives you 56. The last 2 positions together would give you 80, 90, right? So hopefully I didn't make a mistake. 34 plus 50, well actually let's start from here. 5, 8, 13, 13, 21. Actually, I don't have it anymore. 13, 21, so that's 4 and that's 3, 34. 21 plus 34, 5 and 5, so that's not 56. So 55. 55 plus 34, actually this was wrong, so this is not good. So it would give you a 9 and it would give you a 8, 89. So if we would do this inside a, so if you guys see this right now and you would have to do it, let's say we create private static void, actually not void, let's say int for the final result, and this is called the Fibonacci, and we would say a position, right? This is the position I want to get. So if I say position 8, you would return 34. If I say position 4, you give me 5. If I say position 10, you give me 89. If I position 1 million, you'll give me whatever value that is. How would we build this inside loops? Anyone?
Can you please repeat the question?
So given the value 1 and 1 for both starting positions, so position 0 and 1, it's given to you. It's always going to be 1, okay? Now, I'm asking you for any position, and I want you to give me the value of Fibonacci for that position. So if I give you position 0, you should return me 1. If I give you position 5, you should give me 8. And to calculate those values is you take the 2 previous positions to get the value of the current position. So if I wanted the value, let's say of position 6, well, I need to go to the previous position 5, see the value 8, and the position before that, position 4, which is value 5, and I would add 5 plus 8 to get 13. Does that make sense? So if I had to color this, so given the first 2 position, you get all the previous positions. So we have position 0, 1, 2, 3, 4, 5, and 6, let's say. Okay, and it keeps on going. That's the thing about Fibonacci. It was to calculate the speed of rabbit reproduction. And the thing about Fibonacci is the first 2 values are given to you. The first 2 positions is always going to be 1 and 1. Why? Because you need the last 2 positions to give the next one. So to give the value of 2, so to get the value of position 2, so this is position, and this is the value. So to get the value of position 2, you need the value of position this and this. So the last 2 positions. So 1 plus 1, so in this case, let's do here. 1 plus 1 we give us 2. So we're kind of lucky because at the beginning it matches, right? Now to get the position of 3, we need to calculate position 2 plus position 1. So the last 2 positions, right? In this case, we get 1 plus 2, which gives us 3. And for me to get the next position, 4, we need to calculate 3. And we need to add position 2, which would be 3 plus 2. Let me erase that. Just so I could keep the same order. So here we would say 2 plus 3, which gives us 5. And let's do one more just to make sure. So now if you think about it, fifth position, to know the value of fifth position, we need the previous two. So we need the position 4 and position 3. So this would be 3. Sorry for my handwriting, it's a mouse. 3 plus 5, 8. Right? And if I wanted the position 6, we do the same thing. Last one I'm doing. We need the previous position and the position before that. So 5 plus 8 equals 13. Right? Now, how would I code this? Give yourself a few seconds. If you're watching a rerun of this, you could pause the video, take your time, figure these things out.
We have to do it using recursion, sir.
Well, we could do recursion, which would be much cleaner. But if you don't mind, I would like it we start with a loop.
Yeah, sir. So for that, sir, we have to initialize like two variables, number 1 and number 2.
Okay, is that your position?
Yeah, sir.
So
Position 1 and position 2.
how about we give it a good name? Number 1 and number 2 doesn't tell you as much, but if we say int position 1 equals 1.
0, sir, actually.
0, okay.
0, yep.
And int position 1 equals 1
is equal to 1. Yep.
Okay, what else?
Sir, there will be a number 3, which will store the result of the addition of 2.
So a int result.
Yep.
And you want to initialize that to what?
Set to 0.
Okay.
Yeah. So now, sir, result is equal to position 1 and result is equal to position 1 plus position 0, or like vice versa.
So result equals
Is equal to position 0.
Position 0 plus position 1.
Yep. And now we have to swap the position 0 and 1. And now the new positions will be position 1 is equal to result.
Okay, but is this a loop or what are you doing right here?
Yeah, sir, actually it is a loop, sir.
Which part? What do you want me to put in loop?
Sir, the result part.
Okay, so in this part you want a for loop, a while loop, what do you want?
Yeah, for loop.
For loop, okay.
It will start from 1.
So let's say position equals 1. Actually, we already have a position. Let's
No,
say,
sir, actually because we already done the first and second.
Okay.
We already have first and second numbers. So it will be a start from 3.
Okay, so what do you want our variable to be named here? Because position is already given to us. And position 0 and 1 is taken.
We can count, sir.
Count is good. It's just a counter,
Yeah.
so we don't really care so much. Starts at what value?
So 3, because we already have two positions, 0 and 1.
Okay.
Or we can give it 2,
2.
and after that we can use it. And a count is less than position.
Count is less than position.
Okay. Actually, we can give it count less than or equal to position, because we have to.
Let me just move these.
No, sir.
things. 1 second. I just want to move these a bit so you get a bit better view. Okay. Sorry, go ahead.
Count less than or equal to position.
Count less than or equal to position.
Or less than or equal to, yep, and count plus plus.
So no equal.
No, sir, there will be equal.
Okay. And then plus plus position.
Yep.
Plus plus count actually. Sorry.
Yep.
Okay, I hope you guys could see clearly. There we go. Then what? What do we put inside of that for loop?
Sir, that result.
Okay.
Yeah. And below that, it will be position 1 is equal to result.
Position 0, you mean?
1.
1.
Position 1
Okay.
is equal to result. And position 0 is equal to position 1.
Okay.
Yeah. And After the for body, we can return the result.
Okay.
Now, sir, actually we have to, every time we have to return the result.
Every time?
Yeah.
Remember, what does a return do?
Sir, actually we can show the values here, or we have to put this function in the, like, calling this function in a loop.
Calling
Are
this
you
function
getting?
in a loop. No, you can't do that. Well, first of all,
Yeah.
your function is the purpose of this. Fibonacci is supposed to take care of Fibonacci. It shouldn't do
Yes,
more
sir.
or less.
Yeah,
Secondly,
sir.
I'm just going to point out a couple things, okay? I'm pretty sure a few others have the same issues. First thing is, if you hit a return inside of your function at any moment, even if it's inside your for loop, it ends your function.
Yeah.
So having this return result here will force us to only do one iteration and then ends it all. So this is not good. Then you mentioned maybe we should output this to
Show the
screen.
values here. Yep. Exactly.
You shouldn't do that either, because your function says Fibonacci. It doesn't say print Fibonacci. The naming matters. Again, we gotta abide to our rules, right? We gotta make sure that our functions only do what they're expected to do, only what they say they're gonna do. If this was named print Fibonacci to the console or something similar, then it would be perfectly fine, because whoever uses this function, even though they don't read what's inside of it, they know by the name what it's gonna do. But you printing out when it's just Fibonacci like this is doing something unexpected, and this is bad programming. Okay? So we shouldn't do this part. Does that make sense? Now, again, this thing, I don't know if you guys are seeing it, but let's see how it turns out for the computer. Okay? So this factorial, let's say, this again, refactor, extract to method. Let's give start of recursion. Okay, I'm just gonna comment it out as always. Actually, let me put all of this inside of that. Refactor, start of recursion. Okay, and we're gonna comment that out. Now, just 1 second. Over here, we're gonna call. Actually, I want to see my Fibonacci. Let me just move that at top here. Okay, so over here, we want to call our Fibonacci. So I'm gonna output to the screen Fibonacci, and we're gonna give it some positions. And we already have some values here, so we kind of know what value should be at what. So the first position is 0. It's an easy one. I'm gonna do position 1. Let's say position 3, 5, and 6. Right, so 0, 1, 3, 5, and 6, and maybe, you know what, we'll go a bit crazy and we say position 120, and hopefully it will be fine. Cool?
Yeah, and so for 0 and 1, we haven't like put any code in the Fibonacci function.
We have to put what, sorry?
Yeah, sir, extra code for position 0 and 1,
You're
because
gonna
the
tell
for,
me.
yeah,
Well, what do you want me to write?
if position is
At what line?
0 or 1,
At what
it
line?
will return 1.
What line would you like me to write that?
So after result.
So after here?
Yeah, yep.
So line 34 or line 35. If
Position requested is equal to 0 or 1, return 1.
okay, but that's good. You fixed one problem. So let's run this application.
So,
Yes.
we also need to change the initialization of position 1 and 0 inside that loop, because both of them are initialized to the result. It would be position 1 is equal
okay.
to.
Good. Amita, you cut something. Okay, but before I fix that, I want people to see it. So we're gonna run our application first time. So we're just gonna do a run. Stop and rerun. And for these values, we should have seen 1 and 1. This is perfect. 1 and 1. The next one, position 3, should have gave us 3, but it's giving us 4. That's not good. Position 5 and 6 should have been 8 and 13, but we're getting 16 and 32. And position 120 is giving us 0. Okay, let's figure out what the problems are.
So here, After position 1 is equal to result,
What line number? You gotta tell
so
me
we
a
have
line
to
number.
use a like temporary variable here.
Tell me what line number and what would you like me to
So
do?
after result is equal to position 0 plus position 1.
Here?
No, sir.
Tell me the line
Inside,
number. Look at the side. Tell me the line number.
after 40.
After 40. Okay, so here. What do you want me to do?
So we can create a variable here or outside the body. It will be a temp variable.
Temp?
Yep. Is equal to position 1,
Okay.
and so position 0 is equal to temp.
Like this?
Yeah.
Okay. So let's see if that fixes the problem. So we get, here. We get this 1, this is perfect. 3, we get 3, that's good. 5, we get 8. 6, we get 13, perfect. So you got a Fibonacci maker. And if you notice 120 now, it gives us a number. Cool? Any person with a question? Where is our Fibonacci? This is our Fibonacci. No questions? Okay.
And so to print like the series in the main, we have to call this Fibonacci function in a for loop.
Yeah, but we don't want to print it. But yeah, good point. Okay. In this case, we just want to get the values directly and see what they are. More than that, we don't really care. Okay. So right now, you actually created Fibonacci. It seems to work. We're not going to thoroughly test it. And this is your code, okay? We could have optimized the code too, but again, we don't really care about it. Okay? The point being, whatever position we're given, right? Whatever position we're given, we want to keep, we want to reach that position. So we don't know the values of that position until we reach it. So what he did is he started at these early positions, position 0s and 1, and he moved up until he reached position, right? Until count is less than or equal to position. So he reached it, right? Now, this same thing, we could also do it in recursive method. Okay, we could clean this up if you want. So rather than position 0 and position 1, I would like to maybe rename that to previous 1, and this one I would like to rename it to previous 2nd. Okay, and I do this because it makes more sense to me if I'm at this position, the 2 previous ones, what are their values, right? And again, we could have done this even before creating those variables. So we're doing extra step. Again, this is optimization. We don't really need to do this. But as you get further down, this should have been our first check. We shouldn't create a variable if we don't need them, right? So this, we could have actually put that at the top. That was good, right? So if the position is either the first 2 positions, then do that. Then we don't care. Now, what we do need to care is, well, if we're not at the early position, we're starting at 2. So the previous, which is 0 here, the first one, previous 2nd, let's say this guy. Well, we don't need it to start there. We don't really care for that. We need to start it at these 2 specific positions, right? Or we could let the counter do it for us. Either or works out. Okay, in this case, I'll just let the counter he did to do it for us so we could ignore it completely. Okay? And you'll notice that when he's getting the result, he's grabbing the 2 previous positions, and then he's moving his you could say his pointer to the next 2 numbers, right? That's what he's doing over here. That's why he has a temp, to move the arrow to the next one, and that one to move it to whatever it was. Okay, it's again, I would clean this up, but to be honest, let's keep it to his code. Let's go with this. Now, knowing recursion, can you rewrite this into a recursive Fibonacci to get the same results? And if someone wants to do it, be my guest. With that, I could help you out with your code. Notice that learning from your mistakes or me giving you comments on your code, I'm telling you, it's much more worth it than just waiting for someone to do it and then you're like, oh, okay, that makes sense and whatnot. Making mistakes is worth a lot more than not making any. Okay. Anyone wants to take a bite? Now, Fibonacci, okay, I'll do the recursive. So in his loop, what he did was he started at the beginning positions and he went towards the higher positions until he reached the position given. In a recursive loop, let's rename this first of all. Refactor, rename Fibonacci loop. We're going to create a recursive version of this. Private static Fibonacci. And we're going to give it again a position. And if you remember the rule I gave you, it's not a forceful rule, but it's a helper rule. We want to always always the end to be at the beginning. So the first thing we should do is check the end condition, right? The end condition for our Fibonacci is what? Well, if we reach 0, 1, which is the values given to us, the same as his. If 0, 1 is reached, give that value. Otherwise, use that to go up. But in the Fibonacci recursively, what we want to do is rather than going up, we want to go downwards. So you're going to see in a second. So if position equals 0 or position equals 1, we want to return 1 because both of those positions are 1, right? If we are at a higher position, well then now, remember Fibonacci is adding the last two positions together to give you the current one, right? And let's say for number 2. If Fibonacci comes with number 2, well, position is not 0 nor it's 1, it's 2. What we want to do is add the last two positions to get this value. So in this case, we're going to return. I'm going to call itself Fibonacci. The current position minus 1 to get this position 1. Actually, let's do minus 1. Right? So that gives you this value. If you guys are looking, let me do a little circular thing here. So this code right now is doing this one. And I want another one that does this one. So here I'm going to do plus Fibonacci. I'm going to call it the same. And I'm going to give it minus 2. Right? Let me erase the board actually. Clear all my drawings. Actually, no, I don't want to clear my drawings yet. Let's do a selection. Let's just move it. So notice what's going on here. And this is it. Now, if you look at it here, this time I'm starting from the right side and going to the smaller positions. So let's start with number 2. Given number 2, is it the position 0, position 1? It's not, false. Go to here, line 33. You notice it's even giving you a symbol inside the IDE telling you this is recursive. Right? Now, I know that position 2 is formed of position 1 and position 0. So position 2 minus 1 gives you 1. Position 2 minus 2 gives you 0. Right? If we're talking about position 6, well, position 6 is formed of position 5 plus position 4. So 6 minus 1 gives you 5. 6 minus 2 gives you 4. So in this, I would keep going down until I reach the end condition, which is 0 or 1, and then go back up on the call stack. And this is important. And this is important because if you look at my code, this part and this is the same thing inside of a loop. And his code is not so bad. This is actually pretty clean code. Okay, we could probably adjust it a bit more, but that's pretty much it. But this is beautiful code, as it could stand. It makes sense to us, it does the job, and it's pretty well done. Right? But if you look at it inside of a recursive call, oh man, now it's beautiful. This is gold right there. And again, this would be amazing, but it has some drawbacks, and we'll talk about that in a second. But look at it for a moment and let me know if you have a question. So no questions? Okay. Well, the thing is, well, actually, let's test it out. Always, whatever we create, we make sure it works. Otherwise, it'd be meaningless. So we take out that, and now we're calling this specific function. And we're going to run our application. And with that application for 0, 1, 3, 5, 6, 120, we get 1, 1, 3, 8, and 13. 120 is actually different. 5 and 6, 3 and 8. Ooh, okay, so we have some errors. Actually, 1, 3. 3 is 3. 8 is position 5. Position 6 is 13. Okay, that's fine. The last number is not showing. Okay. And we'll talk about that in a second. Okay, but every other number is showing. This one is causing an error. And actually, you could see that our application is not ending for some reason. Right? Actually, to make this a bit more clear. What we're gonna do is, over here is position 1, over here is 3, 5, 6, 120. And if we rerun it, you notice it's showing me position 0, 1, 3, 5, and 6. These are good, but position 120, this is the drawback, it's messing up. Actually, it's not messing up, just give it a bit of time. This is just a bit longer. But it could mess up too. While it's doing it, we're going to wait for the results. Do you guys have any questions? No questions? Okay. Now, do you agree with me that this looks much cleaner? I'm still waiting for that result, but you guys agree with me that this looks much cleaner than this? They're both doing the same exact thing, and this is what we need to understand. They're both doing the same exact thing, but having something much cleaner in our code makes the world of difference. Okay, I'm going to clear this thing actually. Having something cleaner to read, well, again, this might be a bit new to you guys, so it might not look as easy to read. Could be an issue. Sometimes they make something smaller, but it's harder to read. So we wanted to make it as easy as possible to read. This gets to become much easier to read, to understand where it ends, and otherwise return the position -1 plus the position -2 to the same call. And it keeps on doing it until it reaches the targeted amount. Cool? Well, in this case, it has to do all of this, variables and whatnot, to do the same thing. But again, you'll notice a couple issues. Well, first bonus is Fibonacci recursion is much cleaner. Beautiful stuff. And this is why I say this, you're going to see a lot of times in interviews as something potential to use to do your interview. And I find it, anyway, that doesn't matter what I think, but this is something that we would use in interviews because our code becomes much simpler to read, and you do it much faster than if you were to do it inside of a loop. But drawbacks is it's creating a call stack for each one of them, and this becomes harsh on the computer. And notice here it's going and going. It has an infinite amount of call stack to go through. So let's see how this Fibonacci Let's stop this because it's taking forever. Let's see how it does this. So we're gonna put here, we're gonna start at position 0 and we're gonna do all of them, okay? Well, maybe not all of them, but you'll see what I mean. So again, at the top, I'm gonna say run, debug main, having the breakpoint beside. Whoa, what happened here? This is a comment. I can't put it on the comment. Here we go. Let's debug it again. Okay, so our Fibonacci came in with position 0. Notice our call stack currently has the main, and from main at line 17 it called Fibonacci, and we're at line 30 waiting for things to happen. Position is currently 0, so you'll notice right away it's going to return and it's going to print to our console position 0 is 1. That was pretty quick. It worked out fine. Everything's good. We do the same thing for position 1. It's the same value. It returns 1. And we are done. So far, so good. Any questions? If you don't ask the question, I move on, by the way. I hope you know that. Okay. So now we go to position 3. And now it becomes a bit more interesting. At position 3, we're not 0 or 1. So we're not our end. So we're going to call two functions, right, before we return. So the stuff in parentheses must be done before we return. So before we return, notice, we're going to call two functions. Fibonacci position -1, Fibonacci position -2. So we call those. So notice that there's two functions. It's telling me which one would I like to step into now. Let's go to this one. So notice now there's another function on my stack, right? There's actually three things: the main, the Fibonacci 33, and the Fibonacci 30. So this is on the call stack because it has to go backwards, and this is important. Right now the position is 2. We notice position 2 is not any of this, it's not 0, 1. And again, we need to do -1. So now it has to, again, do these two functions. So let's do that one. Now look at our call stack. Is that 3 stuff in the call stack, and we still didn't do the other branch, by the way. And you're going to see what I mean by the other branch in a second. And this time position is 1, so we could return right away 1. We go back up a call stack, so we're going to go to this one. So we're at number 3, we're going to go to number 2. And now we have to do the other thing, the other function call. So we're back again down with position 0, and you'll notice it's going to return. Now we got the two numbers. We're going to go up again one more level, but now we got to do the other function. And you guys are seeing this? Right? So what's going on? Let's draw this for a second. Draw. What's going on here? Actually, let me go back to now. Let's bring this down for a second. What's going on here inside these Fibonacci calls? Let me take a color here. So the first time we call this Fibonacci, let's call it F. We've got to give it a position, the end result we want. So if I give it position 3 as an example, well, to get 3, it needs to get position 1, and it needs to get position 2, right? And for 1, well, 1 is position 1, it gives you back 1. So this returns back right away 1. So this is fine. But when he calls position 2, he doesn't know what position 2 is, but position 2 is F at position 0 and F at position 1. And he knows these two are 1, so he adds this, gets 2, and this returns 2. So 1 plus 2 gives you back 3, right? Now the problem with this type of recursion is, let me erase some of this. What would happen if that position is not 3 or some simple number, but it's a big number? 120. Right? If I give this function 120, well, we notice it's not 0 or 1, so it has to call two functions, which is itself. Fibonacci let's say 118, it's -2, and it has to also call Fibonacci position 119, and it will add up those two numbers. But again, these are two functions, so this function 118 comes back here. Is it the end condition? No. So call the two previous versions. So here it will call F1116 plus F1117. Right? So these two are added together, but again, these are functions, and it keeps on redoing that thing until infinity. And again, this is one branch. So don't forget the 119 also needs to do it. And the stupid part is it's going to do the same function calls. The 119 is going to do the 117 plus the 118. Right? But the 118, we already did it. But the computer doesn't know better. The computer is stupid. So it'll redo this the same as it did here. Right? This thing over here is the same call as over here, but it's going to be redone because the computer doesn't know better. And then it's going to branch out a million times until it reaches the end, before it goes back up to give you the final result. Does this make sense? And again, it looks beautiful compared to the loop. But again, it causes a lot of other issues. And this is why we don't use this in production as best as we can. But during interviews, this is gold for you. Cool? Any questions? Does
So recursion in every case, it is like limited to small number of cases. If we have smaller numbers,
I don't understand your question. One more time.
so in every case, so the recursion is only good for small number of like iterations.
Well,
If
no.
the
Yes. The problem with the Fibonacci one is it has too much to keep going because it's calling the Fibonacci twice, once here and once here. So the amount of using the Fibonacci becomes big, right? And because it can't remember the values at those positions, at least in our case scenario, it doesn't. It becomes really hard on the memory because it has to create a new function on the call stack, right? And it keeps on growing and growing and growing. And then when it comes back down, when it comes back up, it has to take the other branch and again go downwards, which could be infinitely long. So it becomes a bit slow in these cases. You're right, it's good for small numbers, but how do you predict that the user is going to submit a small number, right? When we make our code, we're not predicting that the user is going to put a small number or is going to put a big number. We're predicting our code is going to be correct for all of them. Correct and good and fast and clean. Might have repeated some words there, but it's always this.
So what will be the best approach for that kind of like project?
So the best approach is, if you're in an interview, use the Fibonacci because it's beautiful, it's clean. If you're by yourself in coding, again, you could use Fibonacci because it's clean and you could see how it's doing it. It's simple to read.
Yep.
But afterwards, go back to the loops. Right now, at least, at this moment, you have no idea or reasons to use recursion inside your programs. And if you're, for some odd reason, you're super positive that your numbers or the stack's not going to grow too much exponentially, well, you could still stick to recursion. If you work for someone, you'll notice that most of the time someone's going to review your code. Your code's never going to go in without being processed by some other person. And to be honest, they will always, most of the time, tell you not to use Fibonacci. So if you ever work for me, for example, if for some reason your internship goes to me, I won't allow you to use recursion. Even though I find it beautiful and so on, it's hurting my speed and my performance and other things. Okay, but if you go to an interview at a company, they're gonna give you limited time to create an algorithm. So let's say again, if you would have went to Microsoft or something, you get 40 minutes for each question or for each interviewer, and you usually have 5 interviewers. So within those 40 minutes, not only is he going to talk about your CV, he's also going to give you a question that's much, much, much more difficult than what I'm showing you here, but you only have a limited time. So in those cases, it's good to use recursion, and you might even hint to the interview, I know recursions are bad, but I'm going to just use it in this case because we have limited time. So he's going to be happy that you understand what recursions are. He's going to be happy because you're going to solve his question really fast. He's going to be happy because your answer is going to be clean, right? But in a real project, you want to stick to loops, okay? Until further down the line where you understand a bit more about recursions and, like this, right? We have an issue where position 118 was already solved. Well, there's ways to go around this. We could have stored that data somewhere and seen if we already seen it. Well, then go grab the data rather than calling this, right? In those cases, it would have been maybe fine, but we're not at that level, so we don't really care. For now, recursion is nice, only for interviews and nothing else. And I'm telling you this, there's a reason I keep telling you interviews, because if you go for a good company, they will always test you out, right? You're all gonna get jobs, don't get me wrong. But there's the companies that don't give you any programming test. It's because they're not expecting much, and when they're not expecting much, they're also not gonna expect to give you a lot of money. So you're looking at the low end of the salary chain. But if you go to a company that expects more, well, first of all, they expect more from you. Secondly, they're gonna give you the money that goes with that expectation. So more money equals your knowledge, your your knowledge that you build up, right? It takes you a year to graduate, 2 years to graduate. That's a knowledge that you worked for. They need to pay for that accumulated knowledge. And this is important. Cool? Any other questions?
So any other way so that we can minimize, like to compact the code used in loops?
Not within our current power, not within our current knowledge, and we're not going to touch anything too far out yet. Okay, we're going to learn progressively, and for now, if you don't know it, it basically means we shouldn't touch it.
Okay.
Cool. And something I see a lot of people do, classmates, students, whatever, even colleagues, is they tend to make everything into a one-liner code, thinking that's going to clean up, that's going to make it better. Actually, try not to do that. Try to make good naming styles and use as much space as you need to. You don't need to compact anything. You don't need to make it all into two-liners. This is because of what I needed. The result was two-liners. It's not because I wanted to enforce it, right? You don't need to always have two-liners. Sometimes it'll be 1,000 lines and it'll be so beautiful, it'll take you a second to read it. And sometimes it'll be one line and it'll take you an hour to understand what the hell that line means, right? So you got to be careful with this. Any other questions? Okay, so let's move on from Fibonacci. Let's move on from recursion. So you'll notice that the position 120 actually. Let's put a little red here, just to show you that it was doing it. It was just stuck. Let's restart our application. So we're doing Fibonacci 120 just to show you how this call stack is going to grow. Okay, I'm not going to show you the program too much. So let's go inside that program. Not that one. We want to go into Fibonacci. Okay, so inside Fibonacci, we're at position 120. Go inside. Look at we're at 119. Just look how that call stack is going to grow. Okay, I'm going to ignore which one is doing. And remember that this is one side of the tree. So if we go to the other side, it's huge, right? And eventually, just like the first time we were running this, two things could happen. One, it takes forever. Secondly, we get this thing, this error, this exception called stack overflow. So at some point, there's a maximum to how many things I could have in my stack. And maybe this is gonna reach it. And again, notice these are all calls to my Fibonacci. So they're not finished, the same way as our main is not finished, but they're all calls to my Fibonacci, and it's repeated at least 67 times, right? And it's gonna keep going because again, we had 120, so hopefully at 120, it should slide to start going back down. So we're gonna just try and reach that number. And again, the computer is much faster than this, but it's still slowed down by a lot, right? So we're reaching 110, 112. Look at the position. We're at 5 now. We're still going down. We're still going down. We're at 1. Now, if you notice our call stack, 120 is going to become 119. But don't forget, every one of those is 2 branches. So this at 119, we're gonna have to create another branch for the other one. So 120 again, position 0. We go back down. Now we go back up. And we go back up. But remember, we have the other branch. Now we go back down. 119, 120, it keeps on doing this thing. And now we're gonna be stuck at these numbers as it goes back up slowly. Slowly, for each branch, it goes down and then it goes back up from the 0s and 1s. Right? And this is taking forever. This is the big problem. Cool? And again, even though recursion looks beautiful, it's not something we want to use too much inside the work environment. Okay. Any last questions before we move on from recursion? No questions? Okay, so I'm kind of actually tired of talking. What we're going to do is we're going to take another break. This is our last break, and then we'll go through some stuff, and tomorrow we'll do inheritance and polymorphism, the last bits. So for this for this break, it's 5:34. Let's come back by 6:15, and we'll do our last stuff we need for today. And tomorrow we'll do polymorphism, which is the foundation for your programming skills. Okay, so the stuff I'm talking about right now, all of these stuff, whatever language you go into, you'll see it. The more you'll understand it, the better your foundation is. The better your foundation is, the better you're gonna be in the workplace. Cool? So I'll see you guys back at 6:15. See you guys then. Cheers.